So I'm going to give a very quick and simple introduction to static word embeddings. Topics include word vectors, sparse word representation, and dense word embeddings. Will be a very simple and high-level overview. So, what as a vector? So, in machine learning and deep learning and any other things that we would need to input information into the computer, data like audio, video, image, and text, they will need to be converted into numbers in order for the computer to understand and process. So similarly, we will want to turn words into a vectors of number. But how exactly will we do that? So an important idea in natural language processing is the distributional view of words. So we would want to characterize the knowledge of a word in terms of the company that it keeps. That means we want to represent the word in terms of like the surrounding words. So this is similar to how when you read a book in a new language and you don't understand some word, you would want to read the full sentence that contain that word and try to guess its meaning. So this is similar to that. Because for the word, we can know the information about that word through the surrounding words. So if we have like many contexts where that word appears in, then we can kind of represent that word in terms of these frequently occurring word that occur near that words. So find a word, for a word, find all the contexts in which it appear, and find the context words that share many frequent contexts with that word. Then if we have a large enough text collection, we can have a good count, a good estimate to represent that word. So to formalize this more, representing words as vector. So if we do what I've just described, then we will have like similar words. They tend to have like similar context that they appear in, right? So if we throw all of them into some space, then these similar words will appear nearby in space. So like very good, amazing, all of these are positive words that will like be represented by similar context words, and so they will appear nearby in space. And we can also have something like a relationship between words can be captured by the vector operation. So for instance, if you have the word king and you have the word queen, and in the space we get the distance between the word king and the word queen, then we add that distance to the word boy. Then we will have that word, we will have a word like girl, where like the distance here can be something like gender, and if we add that gender to the boy, then we can have the word girl. So there are two kinds of embeddings. One is sparse vector, which is like a simple count, as I just said, and we also have dense learned word embeddings. A famous word here is word2vec, which I'll briefly talk about later. So sparse vector, representing words with count. So for instance, so for the word apple, we want to have like a large text collection, and in those large text collection, we count the words that appear close to the word apple. So we have like eat, fall, ripe, and other words. And we do the same for orange in the same large text collection. So we also have like eat and fall appearing near the word orange. So each of these context word, we can use them as a dimension in the vector space. A dimension here is like an axis. So for instance, if we take the top two dimension here, with the top two count, we have it as the x-axis and fall as the y-axis. And we use this count as the coordinates. So it here is apple here is represented by 794 counts of it, so all the way here, and 244 of count of fall. So this coordinate 794 and 244 is the coordinate for the word apple. And if we do the same for orange, you would have like 265 and 22, which is somewhere here. So now we have had a way to represent the words in the vector space by the other context words as dimensions. Of course, if we try to check the word similarity by Euclidean space, then it may be impacted by word count. What do I mean by this? So we have the apple, which is a common word, but if we have some other kind of apple like Fuji or Honeycrisp, then that will be like a rarer word. So its count will be like somewhere very low here. Then if we simply use Euclidean space, then we don't have it as a nearby word with the word apple anymore, even though they are all apples. So we can bypass this with using cosine similarity instead, because again, this is word vectors rather than points. So we would want to use the angle between the vectors to capture, to measure the similarity. So the word apple, it will be the word like Honeycrisp or Fuji, it will have a lower count, but it will be somewhere here with a lower count, but the angle between it with the word apple here will be still be small, so we can still capture similarity by using cosine similarity. Okay, some words are more informative than others. So there are words like the, to, of, and these words, they can co-occur frequently with all the other words. So like it can appear in any sentence. And so if we use this as a dimension, then it, like every word will have this dimension with a big count on it, and it can actually drown out more important context. It can drown out the other dimension because the count of these words are simply too big, and it will appear anywhere for any words. So that's why it's less informative, and we would want to use some other some other way of counting and filtering out this word. So we have TF-IDF, that is term frequency, inverse document frequency, and point-wise mutual information. So basically, both of these, what they do is they will divide, like by, so for instance, in term frequency, inverse document frequency, they will try to look for words that are frequent in this document but rare across other documents. So it appears a lot in one document but not in others. So those kind of count will be more informative. So basically, both TF-IDF and PMI, they will divide by the frequency of that word appearing anywhere. So by doing so, because we are dividing by like the frequency of it appearing on every other documents, we are actually like filtering out these words that just appear in any document. So yeah, but the sparse word representation that I have described, how they look like is that they will be a long vector of vocabulary where each entry will be a count. So we will have a very long vector that is the same of like all the words in a vocabulary size. So it's very long, but there will be many entries that are zeros. So because not every word appear in the context of other words, so we will have vectors that are long and sparse. So we don't want this. We would want dense word embeddings. So why dense? In practice, they work better, and we would want short vectors because they are easier to use as features in machine learning. They are like fewer weights to tune rather than like a very long vector. Dense vectors also generalize better than the explicit counts because these counts can change depending on the corpus, right? Yes, they are also better at capturing synonymy. Like so words like car and automobile, there are like many words that are synonymous to one another, but they are represented as distinct dimension, as distinct entry, distinct aces. So we would want like car and automobile to like maybe just be one entry, one dimension, one axis, instead of like having them being separate distinct axes in the vector space. So that's why we would want to move from like a short and sparse vector into dense word embeddings. So how do we do that? So the idea here brought to you by Word2Vec is to predict rather than to count. So instead of like counting how often each word appear near some word, we would train a classifier to try to predict like how likely is this word appearing near another word. So this task, like this prediction task of how likely it is to appear next to another word, this is actually a fake task. We don't actually care about this task, but what matters is that we would want to take the learned classifier weights of this classifier that we have trained on and use them as word embeddings. So this is what like the word embeddings will look like instead of like the explicit count like this. So Word2Vec is actually a very interesting work, but for the sake of time, I want this to be a very brief introduction. I will not go into detail of that. So we'll move on to the limits of static word embeddings. So what we have been doing is that we are representing each word in the vocabulary as a single fixed vectors. But in reality, language is very context dependent. So the word bank here, we have like river bank and we have financial bank, but this single word bank will use the same vector. So how do we differentiate that? And he runs a company versus he runs fast. Also, different words, different meanings, but the same vectors. These different words depend on the context. So, static word embeddings here cannot adapt meaning to the sentence context. It's still a fixed vector and not flexible at all. So this is the motivation for contextualized embedding that can like dynamically adjust the word meaning, adjust the vector based on the surrounding words. So I hope to have a video on this in another in the future. Thank you for listening. So yeah.